Now we're going to turn our attention to alternating series, and those are series in which the terms alternate between the positive and negative. And just to give you a sense of how the convergence happens when they do converge, I've graphed here for a few examples the partial sums. So this is n, the x-axis, and this is the nth partial sum. And you can just tell by the graph here that this series looks like it converges to some number, like right around 2, it looks like. And likewise for the one below, it looks like this series, which is the alternating harmonic series, converges. And it looks like it's converging towards some number, I don't know, around 3 or 4, somewhere between 3 and 4. So that's one thing to note, is just the behavior of how alternating series converge, right? They will approach the limit from both sides. They sort of dance around it. And that's going to be important, especially when we start talking about the error we can have when we're using an alternating series to approximate a function. Now, of course, not all alternating series converge. This one here shows that alternating behavior, except that it looks like the partial sums are sort of, I guess diverging is the word. They're spreading apart from each other. So this would be a divergent alternating series. And the reason for that is because if you look at the limit of the non-alternating part, that's going to 1. So it's as though in the long run the terms are going back and forth between 1 and -1. And we've already seen that the series -1 to the n diverges. So any term that is approaching 1 or -1 that is part of an alternating series is going to behave the same way. So I've mentioned before that there are 2 types of convergence that we're going to study. There's what's called absolute convergence, and then there's conditional convergence. And I think I might make another video to really highlight the distinction, because it's one of those things I think that students, they don't understand, because not enough time is spent in giving them a sense of the difference. But for now, we're just going to understand that conditional convergence is a weaker type of convergence than absolute convergence. So if something doesn't converge absolutely, it still has a shot if it's an alternating series. It just has to pass the test below. Again, the main difference between conditional and absolute convergence, it has to do with how you add up the terms. A series that's absolutely convergent means that you can add the terms up in any way and you'll still approach that limit. Whereas a series that only converges conditionally the terms have to be added up in a very special way. So that's, in a nutshell, the difference. So this is all that has to happen for an alternating series to pass the alternating series test and hence converge. You need all the non-oscillating terms to be positive. You need the non-oscillating part of the terms to be decreasing, which is what this says. And not only do they have to be increasing, they have to be going to 0. If those 3 things are true, then your series converges conditionally. I mean, it might converge absolutely as well, but it at least converges conditionally. So how would we apply this test? Well, first of all, when you do analysis on problems like this, you want to check for absolute convergence first. So I'm going to do that here. I'm going to see if this converges absolutely. So let's see, absolute convergence. Well, the absolute value of that term is that guy. But that's familiar. That's the harmonic series, which we know diverges. All right, so it does not converge absolutely. So let's check conditional convergence. So let's see, are all the non-oscillating parts of the sequence of the series positive? So that would be these terms right here. That's a sub n. So let's see, 1 over n, are those all positive? Yes, those are all positive because we're plugging in values from 1 to infinity, and 1 over n will always be positive. You might wonder what situations would show up where that's not the case. Well, like cosine of n, that would be a situation where you're not, the terms aren't always positive, right? Because cosine oscillates between -1 and 1, depending on the value. Are all the terms decreasing? So is it true that the nth term is bigger than the n plus first term? I think we can see that that's true for all n. So far so good, and then we just have to show that the terms go to 0. Well, the limit as n goes to infinity of 1 over n is equal to 0. So all three conditions are met, and we can say that this converges conditionally. Okay, so you want to get into the habit of always checking absolute convergence for an alternating series, and then if it fails, then you'll try the conditional convergence test. And here's a case where it passed. Now the nice thing about alternating series is that they're easy to analyze for error, which is to say that if you were going to use, for instance, if you were going to use, like let's just give as an example, we know that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So let's say we were going to use we wanted to approximate sine of 2. So if we were going to approximate sine of 2, let's say we're going to use the 5th degree Taylor polynomial. Then that means that sine of 2 is about equal to whoops, that's a negative. Sorry. All right, so sine of 2 is about equal to that. Now, they're not going to be exactly the same, and if we want to know what the error is, we can understand it through a diagram which emphasizes how an alternating series will converge. We saw some pictures before about how it's going to approach the limit from both sides. I'm going to draw a more one-dimensional picture here. I'm going to do it over here. So, like, let's say you've got your alternating series written above, and we're going to start to use the partial sums to see how they approach a certain limit. So let's just say this is a number line, this is 0, and let's just say that this is the limit. So we're just going to graph the partial sums now. So the first partial sum would just be your first term. So you just add the first term, and that looks like this. Now that's going to overshoot. That's going to overshoot the limit. In fact, I'm going to emphasize more that it overshoots it. It's going to overshoot the limit. So then we look at the second partial sum, which is a1 minus a2. Well, the second partial sum is going to land, so again, the first partial sum lands here. I'm going to relabel this as what the actual sum is. So that was a1. a sub 1. The second partial sum, well, we're adding a 1, and then we're going to subtract a 2. So that ends up right around here. So that's the second partial sum, and this is, subtracting a 2. And now we're going to add a 3 for the third partial sum. So that would be a1 minus a2 plus a3. So that brings us here. And so what did we notice? Well, it looks like the sums are just dancing around the limit and approaching from both sides. So that tells us something about the error. So for instance, like let's say I wanted to know that the error, I want to look at the error when I'm using the third partial sum. Well, the third partial sum is here, and this is the error. This brown line here, right? That's the difference between. Right, it's the absolute value of the difference between the actual limit and the partial sum. Notice that's going to be less than the fourth partial sum, because the fourth partial sum is going to shoot me back past the limit I'm sorry, I think I did said it was less than the fourth partial sum. That's not what I meant. What I meant was it's less than the fourth term in this series, right? Because this length right here is certainly less than the length of a sub 4. And so that gives us a convenient test, which is stated up here, right? So in our example above, we can say that, well, if I was going to use the fifth partial sum to approximate sine of 2, we know that sine of 2 minus the fifth degree Taylor polynomial I'm using, evaluated at 2, right, that difference is going to be less than the next term, and the next term is going to be negative 2 to the 7th over 5 factorial. So again, we ignore the negative because we're making a statement about length, but it's going to be less than this. Okay, so it's a very easy test. It's a very easy test to apply. You know that the error is always going to be less than the absolute value of the next term if you consider the alternating part of it. So questions can be worded in different ways. This example says, find the bound for the truncation error after 100 terms for this series. So we've seen the series, we know it converges. And what would the truncation error be? In other words, what if we were going to use the 100th partial sum, how is that, by what amount does that differ from the actual sum of this infinite series? And so we can use, this test is very easy to use because let's say that this converges to L, to the limit, then the error is just the difference between that limit, and if we're using the first 100 terms, then it's the difference between the 100th partial sum. We know that's going to be less than the absolute value of the next term, which would be S sub, 1 over 101. Right, so that's the 101st term because the 100th term is 1 over 100. So, so there we go. So there we know that the error is bounded by 1 over 101. So we are within 1/100th of the actual error. I mean, of the actual sum.